The title of today's notes is complex numbers. And what I mean by complex numbers is this is often referred to as like imaginary numbers. They include imaginary numbers. So if you want to write imaginary, that's what I mean by complex. So the first thing that I just want to put out there is that complex numbers, and this does become more important with the web homework site, the standard form for writing a complex number is this form, A plus or minus BI. So the order does matter. And you have your, constant component or your real component first. Followed by the imaginary component. So when you're typing your answers in, it is important that you have it in this order and you're not putting the imaginary component first. So just getting into this, complex numbers is when we enter a realm of mathematics that is a little bit bizarre. You work with the numbers, you do all sorts of things, and then it's like, in a situation where you think that it would just be no solution, yes, Bryn, you may move up, or I can make this a little bigger too, or both. So instead of saying, oh, no solution, we actually enter into this realm where it's like, actually, we can keep going. We're just going to use an imaginary number. And so this does have applications that you generally don't get into, like in a high school setting, with like vectors, and there's a totally different plane. Oh goodness. Where we get I is from when we were taking the square root of a negative number. So if we were trying to define what I is and how it comes into play, it's that I'm gonna put this over here. I equals the square root of -1, okay? So normally, when we encounter a 0 in the denominator of a fraction, we just say undefined, no solution. But when we encounter a negative number under a radical, we don't just say no solution. We can turn it into a complex number and a complex solution. So I is the square root of -1. And so we can then follow that I squared would be the square root of -1 times the square root of -1, which would be what?
1. No, not 1. I don't know.
It would be -1, right? If I take the square root of -1 times the square root of -1, that radical essentially lifts and I get -1. So I is the square root of -1, I squared is -1. And then if we have I to the third, square root of -1 times the square root of -1 times the square root of -1, that equals, this is -1 times the square root of -1, which is I. So this is -I. And then finally, we'll take it up to I to the fourth. This is -1. This is -1. Okay, that's how we get 1. There we go. So the reason we're walking through these, there may be questions you encounter where it says I to the something, and you have to simplify it. So this is just showing you a couple iterations of how we can figure out what it would be. If we have I to the 10th, you would break it down in this way. But just knowing that I equals the square root of -1, is pretty essential information. So we can also do operations with complex numbers. So that's also what we're going to work on. So adding and subtracting, we can add and subtract complex numbers. And this works very similar to things we've already talked about, such as polynomial operations and operations with radicals. We'll see some similarities between that because essentially, we have the square root of a -1 is I. So we'll see some similarities of things we've already dealt with here. So in order to add or subtract, it's pretty simple. You put the real parts together and the imaginary parts together. So essentially you're combining like terms. That's probably the simplest way to describe it. So we add or subtract the real components, and you add or subtract the imaginary components. All right, so we could do an example here. Let's take a look at 5 minus 3i plus 7 plus 4i. These are often written in parentheses to show that like this is the complex number because it has those two parts, but the parentheses really don't matter as far as when we're doing this operation of addition here. So we're going to combine the real parts. So I've got a 5 and a 7. Those go together. So 5 plus 7 is 12. And then I combine the imaginary parts. So negative 3i plus 4i just gives me a positive 1i or I. All right, so that's pretty straightforward, right? We would want to be careful that if we are subtracting, we would want to distribute. So I'll do a quick example of that. So if we have 7 minus 3i minus negative 2 plus 8i, just like if we were dealing with anything else, this negative needs to be distributed through the second parentheses here. So you would maybe rewrite this first. 7 minus 3i minus negative is a plus 2 minus 8i. And then we would combine the real parts. 7 plus 2 is 9. And the imaginary parts, negative 3i minus 8i is negative 11i. Feel pretty good about that? Okay. So addition and subtraction is pretty straightforward. We can also multiply and divide complex numbers. So when we're multiplying, talk about multiplying first. When we're multiplying these complex numbers, we're going to treat them similar to how we would binomials or polynomials. And so we're going to be using distribution or FOIL in order to solve these. So if FOIL is the word you like to think of for that, can write that down, or just the word distribute. We will just see one thing that's different from these than just a typical polynomial is that there will be an extra step of simplifying. We want to remember if we see an I squared at any point and if we multiply and get an I squared, that can simplify to -1, which will enable me to simplify further. So that is the one thing you will encounter when multiplying that we'll want to keep in mind, that I squared equals -1, and we'll use that idea to further simplify. So I think just seeing an example is probably the easiest way. So if I have -3 plus 2i times 4 minus 9i, we're going to distribute. So I'm going to pass out -3 first. -3 times 4 is -12. -3 times -9i is a positive 27i. Then I'll distribute this 2i. So 2i times 4 is a positive 8i. And then 2i times -9i squared will be a -18. Sorry, 2i times -9i will be a -18i squared. So this is where this idea comes in. So I squared really means this is the same thing as -1. So this can create a real component. So I have -18 times -1, which is a positive 18. So however, I don't mind if you don't write these as separate steps, like changing the I squared to a -1, multiplying it out. Like that could easily be 3 different steps that you have to show. But do make sure that you're indicating how you're getting from here to here somehow. Show that you understand that transformation is happening. And so then we can just combine, sometimes how I do it so I don't even have to write a whole extra step is I might just write this turns to positive 18 instead of that, and then I can just combine. So then I have -12 plus 18, which is positive 6, which will come first because that's my real component. So I'm combining just to show what I'm doing here. -12 plus 18. Everyone clear how I got to plus 18 from what I originally had? Okay. So -12 plus 18 is 6. And then I combine my imaginary components, 27i plus 8i, which gives me a positive 35i. That would be my final answer here. Okay. How do you guys feel about that? Same as multiplying two binomials. It's just this little thing over here is the only new idea. That if you have an I squared, you're going to change that to a -1 and continue simplifying. All right. When we are dividing complex numbers, this is going to feel very similar to when we're working with radicals. In a similar way, we can have the conjugate when we're dealing with imaginary numbers, and we similarly have to rationalize denominators. So if you have a fraction with complex numbers, then we do have to get it in simplest form, rationalize the denominator to get rid of the imaginary numbers in the denominator. Essentially, we want our final answer to always look like this, a plus or minus bi. We don't want to have i's on top and i's on bottom. So let's see if there's any notes. We just want to make a note about you will want to know that vocabulary of the complex conjugate or just the conjugate. And so if we have our imaginary number z equals a plus bi, the complex conjugate, which is the math notation is z with a line over it, would be a minus bi. So the only thing that's changing is the symbol on the inside. I remember last year some students would try and change the sign out in front of the real part as well. You don't need to do that. It's just the sign on the inside that changes. And the significance of this is that it can be used to rationalize. Okay. So let's just get into some examples of this, which I think will make it easier to understand. If I have 2 minus I over 3 plus 2I, the main idea here with division is we're not actually really dividing anything. We're just rationalizing. So I want to multiply both top and bottom by the complex conjugate. On the web homework, I previewed it a little bit myself yesterday, and there may be questions that are broken into part A, B, and C. A might say, given 3 plus 2I, what is the complex conjugate? So what would be the complex conjugate of this complex number, 3 plus 2I?
3 minus 2i.
Yeah, 3 minus 2I. So we're going to multiply on bottom and on top. So when I do this, I'm going to distribute just like I would when I'm multiplying. So 3 times 3 is 9. I'm actually just going to do this down here, and then I'll write my final answer over there. 3 times negative 2I is negative 6I. 2I times 3 is a positive 6I. And 2I times negative 2I is a negative 4I squared. So just like when we're working with radicals, the reason that the complex conjugate works for this purpose is that look what happened to these middle terms, my imaginary components. What happened when I multiplied by the complex conjugate? I'm able to cancel out that imaginary part. And then it may seem like we still have an I, but remember I squared equals what? Just like we did up here, this is really a negative 1. So what I have here is 9, and then negative 4 times negative 1 is a positive 4. So I have 9 plus 4, which is 13 in the denominator. And then I'm going to distribute on top as well. So 2 times 3 is 6. 2 times negative 2I is negative 4I. Negative I times 3 is negative 3I. And negative I times negative 2I is a positive 2I squared. So in this case, the I terms don't cancel each other out, which is fine because we're in the numerator. These will just be combined. And then once again, I want to remember I squared is really a negative 1. So I have 2 times negative 1 up here, which is a negative 2. So 6 minus 2 will give me a 4. Negative 4i minus 3i is a negative 7i all over 13. Now, I believe, I feel like on some things, this is an acceptable answer, and some things it's not. I can't remember if on the web homework this works. I feel like we need to further simplify. I think that on the web homework and everything, it really wants it to look like this, A plus BI, which ours really doesn't look like that right now. We have A plus BI on top, and then we're dividing by a number. So in order to simplify this, what we would do is we look at each. So we can do 4 divided by 13 and write that. And then we have minus, and then 7i over 13. Or 7 over 13i, I guess. So now our answer looks like the form that it should be, A plus or minus BI. So I think on the web homework, it wants it split. So if I say like split the fraction, that's what I mean. And if 4 over 13 could simplify, or 7 over 13 could simplify, you would go ahead and do that. All right, how do you feel about that? 1, like, I don't really know. I've never really seen this before. I'm still uncertain. To 5, like, oh, I feel really good. I've seen this before. Feels familiar. And it's somewhere in the between this, fine too. Okay. I'm going to do one more example on here that is one that I probably would have been like, I'm not sure. And then we can take a look at web homework. So here's another one where we're dividing or rationalizing. I have 5 plus 2i on top, all over 3i. So the thing that makes me go, is the fact that this doesn't look like a complete imaginary number. It's missing its real part, which we could just imagine is 0. This is like 0 plus 3i. And so this is a positive 3i. In order to rationalize this, I'm just going to multiply. Essentially what we're doing is we're taking the opposite of the imaginary component. So in order to rationalize this one, I would multiply by negative 3i. I'm trying to think, like, I feel like you could just multiply by positive 3i as well. If your goal is just to get rid of the I feel like you could do either. Don't you think? I don't know. I'm just saying, if I'm thinking about this, I feel like in this case, it's not really going to matter if you multiply by, because our goal here is to get an I squared that'll turn into a negative 1. I feel like you could multiply by either positive 3i or negative 3i. And in the end, when you're doing it on top and bottom, the negatives and positives would work out in the end. That's my thought. Because I'm like, why would you have to do negative? So I think either way it would work. Your goal is just to get rid of those i's in the denominator. So when we multiply these together, I'm just doing 3i times negative 3i. Down here, I get negative 9i squared. I squared is really a negative 1. So negative 9 times negative 1 is a positive 9 on the bottom. And then on the top, I distribute negative 3i. So 5 times negative 3i is negative 15i, and 2i times negative 3i is negative 6i. And so I would get negative 21i over 9. So I'm going to think if that was a positive 3, we would end up with negative 9 on the bottom, and I think a positive 21. So it wouldn't really matter if this was if I multiplied by a positive 3i or a negative 3i. Yes, Zach?
Would it be negative 6i to the square?
Yep, thank you very much. Here we go. This is negative 6i squared, so this can be simplified further. Thank you. So going back over here, this is a negative 1. We've got negative 6 times negative 1, which is a positive 6. So negative 15i plus 6. I want to switch it so I have 6 minus 15i because I want my real part to come first. Thank you for that catch, Zach. I appreciate it. And then just like we did before, we do want to further simplify this by splitting the fraction up. So the first part we have 6 over 9, which actually can reduce. They're both divisible by 3. So I have 2 over 3 minus, then I take this part, 15 over 9 can also reduce because they're both divisible by 3. So I have 5 over 3 I.